So this is our guest lecturer for this lesson. This is Vasya. He's the one that's usually on my lap. Sometimes it's Sergeant Pepper, but he's excited about doing some logic analysis with you today. He's going to be here for part of the lesson. Hopefully he'll decide to go do something else. I don't know. So this is activity 2.1.2 in digital electronics. And I have a little blurb over there to the right. The words frame generator or frame generator introduction appear on this title slide, and nowhere else in the entire slideshow do these words come up, nor do I remember hearing them in my class this summer. And I don't know what that is. I don't know what it's an expression for, but they're on this title slide, and I decided not to delete them because they sound cool. But I don't know what they're going to be about. Okay, so this lesson is on combinational logic circuit analysis, and that's my little blurb up at the top there to give you an overview of what exactly we're trying to do and why we're trying to do it. So while a lot of electrical engineering revolves around designing a circuit to perform an intended function, like somebody tells you this is what we need the circuit to do, and go ahead and design and build it. I was actually just reading an article in the paper today about roller coasters and how when they go to they do either the lap bar or the shoulder harness, they check it, and all of those are connected to some kind of circuit to make sure that every seat that has a person in it, that it actually has made contact and it's secured before the operator of the coaster can actually release the ride to go. And so there's like a safety thing in there. As I was reading it, I thought, well, that's a combinational circuit that does the safety there. So a lot of your engineering is designed around is like, here's what we need the circuit to do, figure out how to build it. But a decent amount of time is spent analyzing existing circuits to determine their function. So you're given a circuit and then you are asked, what does this do? Like, break this down, generate the truth table, generate the logic expressions for an existing circuit. So why that's done, often done in reverse engineering, which is the process of basically pulling stuff apart. And so if you worked for a company, you might reverse engineer a competitor's product to see how it works and to determine if improvements can be made to it. And so you would pull apart something that already exists. Certainly in the military, if the military gets their hands on some competitors like weaponry or programming, they're going to pull it apart and try to figure out, what is this? How does it work? And what can we do with it? So it's also really good in terms of developing your analytical thinking skills. So the actual content doesn't always transfer outside of the engineering, but the thinking skills can. The way that you look at something and then break it down into these smaller parts to try to figure out what it does. So given a circuit, you would determine the circuit output's truth table and their logic expression, determine the circuit's intended function, what is this circuit supposed to be doing, and then determine whether a circuit is working properly. So all of that would be a reason why you would take an existing circuit and pretty much break it down and analyze it. And I thought that was worth mentioning at the outset. Otherwise, this can seem like a really weird lesson to do. All right, so the circuit analysis techniques, there are two main circuit analysis techniques here. One is to go from the logic circuit to extract the truth table from it, and then from the truth table to come to the logic expression. The other is kind of going the other way. You take the circuit, you generate the logic expression, and then go to the truth table from that. Which way, and we're going to work through an example of each of these. We're going to do an example, and then there's like a practice that we'll do in the lesson of each of these. Which one you want to do in a given situation really depends on the circuit and the overall goals and context of the situation where you'd be analyzing the circuit. But both are skills that are worth having. So circuit to truth table to logic expression. This procedure is worth writing down, which is not the same as taking a picture. So writing something down stores the information in this memory. Taking a picture stores it in this memory, and it turns out that this memory and this memory are not actually the same thing. So this is actually something that is worth writing down, picking up the pencil, devoting a page of your notebook to writing down what this process is. So to go from the circuit to the truth table, you would add test points at the output of every gate. And so if you have tons and tons of gates, this is where you might say, I'm not into this. So you might not want to go about it this way. But then you would add a column to the truth table. So you start the truth table with your binary counting of however many inputs you have, and then you would add a column to the truth table for every test point. And that's where it can get to be overwhelming. If you have like 30 gates in your circuit, you definitely don't want to have like 30 columns in your truth table. Then working from the inputs to the output, complete the truth table for each test point, ultimately ending in the circuit's output. And I'm going to highlight that because the way they do this is like, I think, kind of awkward in the curriculum and in the PowerPoint. So it ends at the circuit's output, but they put the output like right next to the inputs. Just the layout is a little bit weird. And then use the completed truth table to identify the midterms from the truth table where the output is 1, and use the extracted midterms to write a sum of products logic expression, which is what we did in the last lesson. So here we have one. It says use the logic circuit shown to write the circuit truth table, and then use the truth table to derive the logic expression for the output F1. And that answers the question, like, what is this circuit intended to do? What do we want that output F1 to be? And so there's our circuit. And so you add a test point at the end of each gate. Make sure that you label like test point 1, 2, 3, 4, and so forth. So you add those test points there, and you know which point goes with which location in the circuit. We have 1, 2, 3, 4, 5 gates. 1, 2, 3, 4, 5, 6 gates. I can count. Honestly, I can. 6 gates, and so the final output would be the F1, the output of the circuit. So there's like 5 test points. And then I actually did this. I moved this. I know you guys can't see under my face, but at least if I get rid of my face, I can see under my face. I moved this. They had this truth table taking up the whole slide, and I thought, well, that's like really hard to kind of picture what's going on. So I moved the circuit from the previous slide over here. And this is where I said here the placement of the column F1 is a little awkward. They're putting the F1 column here, even though that's the last column that you would fill out. So just to see what they did. Let's look at test point 1. So test point 1 is an inverter, comes out of the inverter, and it is the input X that is being inverted. So if X is 0, test point 1 should show as a 1. And so you can see that where I'm pointing with the highlighter. If X is 1, then test point 1 would be a 0 because it's inverting it. Now let's look at test point 2. Test point 2 is the output of an AND gate, and the inputs to that AND gate are test point 1 is going in, and Y is also going into that AND gate. So an AND gate, if you recall from a much earlier lesson, an AND gate will go high only if both of the inputs are high. And so let's look at this. The inputs are Y and test point 1. So right here, Y is, well, actually, this is how I would do it. Test point 1 is low in all of these. So actually, as long as test point 1 is low, it doesn't matter what Y is, because in order for test point 2 to go high, they both have to be high. And so you can just automatically fill in test point 2 is not going to go high in any of those cases because one of the inputs is low. Now we'll look at when test point 1 is high. And what we're looking for is when is Y also high? Well, in this situation up here, you've got Y is low, and so that's not going to send the AND gate high. and here y is low again. But right here in these two rows, if you look at where my laser pointer is, both y and test point 1 are high, and that's the only case where test point 2 is going to be high. Okay, moving on to test point 3. Test point 3 is the output of an AND gate, and the input to that AND gate is test point 2 and Z. Right there. Okay, so test point 2 and Z. Now this can be fairly easy to do here because we've got Z and we have test point 2, and the good news here is that test point 2 is almost never high. So test point 2 is only high in these two situations. In all the other situations, test point 2 is low, which means test point 3 cannot go high. It's the output of an AND gate. And so you could automatically on your truth table fill out 0, 0, and then a bunch of zeros down here. And the only part that you need to look at is when test point 2 is high, and we're going to compare that over with Z. In this row, Z is low, so test point 3 will be low. In this row right here, where Z is 1 and test point 2 is 1, that's the only time when both of the inputs are high, and so that's the only time when test point 3 is going to go high. Test point 4. I didn't notice this. I was like expanding the boxes so we could see the TP4, and I realized like the arrow doesn't really point to the right spot. This is supposed to be the output of the inverter right here, and if you look and follow where that goes, that is the inversion of Y. Okay, so if I look at y goes 0, 0, 1, 1, 0, 0, 1, 1. If I'm going to flip that, it would be 1, 1, 0, 0, 1, 1, 0, 0. And if you come over here and look at test point 4, you see that that is indeed the case, 1, 1, 0, 0, 1, 1, 0, 0. So now let's look at test point 5, which is the output of this AND gate. This is going to be the output of T4. Okay, T4, and the other input is coming over here from the X. Now, it's an AND gate, so as long as one of the inputs is low, the output of the AND gate is going to be low. So what I'm going to notice right off the bat here is that X is low in all of those cases, which means that the output for TP5 has to be low. Now X is 1, so now I have to come over and look at TP4. TP4 is high right there, so that means both of the inputs are high, okay, and which is going to send TP5 high. Here, TP4 is low, which means it cannot go high. And so TP5 gives us all of those. All right, and that brings us to our final column, which is F1, which is just, again, it's a weird spot to put your F1. F1 is the OR between TP3 and TP5, which means this will go high if either one of them is high. And so for TP3 goes high in this row right here, which will send F1 high, and that's not going to send F1 high any other time. Then looking over here at TP5, we have 2 1s here, which will be enough to send it high, and there they are. Everywhere else, it's a 0, and so your final output for this is 0, 0, 0, 1, 1, 1, 0, 0. Kind of a long process. You probably would not want to do this if you had any kind of circuit that had like lots and lots and lots of gates. It's bad enough with a circuit with like 6 or 7 gates, but if you get up to a circuit with hundreds of gates, you would not want to do this process. You'd have to break it down into more manageable chunks. All right, so here's the completed truth table, and then we would identify the min terms from that. So there's only 3 rows where the output is high, and that's at X bar, Y, Z, X, Y bar, Z bar, and X, Y bar, Z. And, okay, yeah, they're not doing that yet. And then you can write this, the logic expression for it as a sum of products. So just add those products up. Now, some of you might be noticing, and the reason why I paused earlier there for a second, that you can simplify this, and honestly that's like where this whole unit goes, is because you don't really want to have something that long. But you might notice that you have like x y bar here and then x y bar here, and it actually doesn't matter what z is. It goes high whether it's z bar or whether it's z. And so if any of you are looking at that and saying, well, couldn't you just do x y bar instead, the answer to that is yes, and that just gets into some of the simplification. So here we have one that says, try to produce a solution before revealing the solution, analyze the circuit, logic circuit shown to produce a truth table, and then write the logic expression for F2. What I don't remember is what I have on the next slide. And I can't go and look at the next slide. So I just can't, one of them I put in another slide for the purpose of doing this, but I don't think it was here. So let's go ahead, and I guess we might as well just start to work this out. So we'll call this point 1 right here, 2, 3, 4, and 5. Awesome, awesome, awesome. And we need to set up our truth table, and I know you guys won't be able to see under my face over there, so it's gonna be nasty here, so just bear with me. So we have 0, 0, 0, 0, 0, 1, 0, 1, 0, and 0, 1, 1. Then we're gonna need point 1, point 2, that's a 2, point 3, not doing that. I can probably do this better with my finger. Point 3, point 4, point 5, and the final function output. And then I have to do this again. We have 1, 0. Oh, seriously, that might be easier to do with the mouse. 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. And then we have 1, 2, 3, 4, 5. And the last column is going to get stuck behind my head. I'm sincerely sorry. I'll be sure I say them out loud. Okay, so here we go. Number 1. 1 is the inversion of A, so we want to make sure we're clear on what these are. So 1 is the inversion of A, so if A is low, 1 is high, and if A is high, 1 is low. Awesome. Okay, 2 is the ANDing between 1 and B. And so I'm just going to come over here. If 1 is low, there's no way something that's being ANDed with it could be high. So I'm going to just take this nice little shortcut right here and fill that in. Now over here, 1 is high, and we're going to AND that with B, and the only place those two are high are right here. Here, the B value is low, and so that's not going to work there. 3 is the ANDing of 2 and C. Oh, cat, go away. This is the mean one. So the one that's by my feet right now will bite me. So I'm going to be distracted. All right, so 3, here we have the 2 low, so the 3 is going to be low right there. And over here, 2 is low right here, so 3 can't be high. Here the 2 is high, so I'm going to come over here and look at my C value. Here C is low, which means the AND gate can't go high, but here is the only place where they're both high. Now 3 is one of the things that is going into my final gate that like to get the F2. So I'm going to just highlight that, make that column a little bit easier to see. Now let's look at 4. 4 is the inversion of C. Okay, so if C goes 0, 1, 0, 1, 0, 1, 0, 1, the inversion is going to go 1, 0, 1, 0, 1, 0, 1, 0. 5, we are ANDing, what is 5? 5, we are ANDing B with the output of 4. So what I'm going to do quick is if 4 is low, 5 has to be low, and those two columns are right next to each other. So I'm just going to go ahead and fill that in. I'm trying to make it easy on myself. Now all that I have left is when 4 is high, and so I just need to compare that with B. Here B is low, but here B is high. Here B is low, and here B is high. And let's go highlight that column. And then my final output right here is the OR between oh heck no. No, you gotta go. You gotta go. I love you, but you gotta go. Bye-bye. Go eat some food. Use your little box, something. Okay. And that's why I highlighted those two so that we could just see them more clearly. If either of them is high, then if it's an OR gate, the output will be high. So in this first row, they are both low. In the second row, they are both low. In the third row, one of them goes high. In the fourth row, one of them is high. So 5 is high here, and then 3 is high over here. Over here, I'll see if I can wedge this in around my picture. They are both low. They are both low. Here, 5 is high, and here they are both low. And so that F column, and I know this is really messy here, but the F column goes 0, 0, 1, 1, 0, 0, 1, 0. So 0, 0, 1, 1, 0, 0, 1, 0. And there's their step. And 0, 0, wait a minute, 0, 0, 1, 1, 0, 0, 1, 0. Gotta go find their F2. It's just like, it seems like a weird spot to me. Wherever you put it in your truth table, make sure that it's clearly labeled, because otherwise I will not find it. So there we go. Now the last step here was finding where you have those 1 values, and there's 3 of them here. This would be A naught, or A bar, B, C bar. This is A bar, B, C, and this is A, B, C bar, and then we're adding them together. I think that part of the process, is a replication from what we were doing in a previous unit. Okay, second direction. This is using the circuit to get the logic expression and then go to the truth table from there. I think well, you might like this better. So you proceed from the inputs to the output to write the cumulative logic expression at the output of each gate, concluding with the expression for the circuit output, and then use the circuit output logic expression to derive the circuit truth table. And you don't have to deal with all the test points, which makes this like a lot faster to do. So this though, this you kind of need if you're going to come up with a logic expression. So here we have our circuit here. And we've got like the XYZ. We have the inverter, the AND, or the OR, and the OR. What they don't like tell you is that an inversion is expressed with the bar. I think that's pretty intuitive because we know that that means like the not or the negated value. And is expressed as multiplication. So whatever you have coming in on the 2 branches of the AND, you write that as a multiplication. And then an OR is expressed as addition. They never said that, which you kind of need to know if you're going to write the logic expression. So, so we have the OR is expressed as an addition. So here's how we trace this through. So we've got X, if it goes to the inverter here, it's going to become X bar. And then the inputs on the AND gate are the X bar and the Y, and that is expressed as multiplication, meaning those are ANDed together, and those are going to be the input over here. The input on this other AND gate right here is just a Z, and so just like multiplication, you have X bar, Y, Z, get ANDed together. Here, this is the inversion of the Y, so this is Y bar, and this gets ANDed together with the X, to give you X, Y bar. And then the OR gate is expressed as addition. So whatever your two inputs are on your OR gate, they become added together. So we have X, Y, Z, X bar, Y, Z plus X, Y bar. And so that's the logic expression. Then you can go straight from that to your truth table. The most tedious part of that is just setting up your count from 000 to 111, and then you don't have to do all the test points or anything. You can go straight to the output of the whole circuit. And so here's the X bar, Y, Z, and then this goes back to the previous lesson. If you have X, Y bar, it means it doesn't matter what the Z value is, and so it would be X, Y bar, Z bar, and X, Y bar, Z. Both of them would have to go to a 1. Okay, so this was the one where I added the extra slide. So try to produce a solution before revealing the solution on the next slide. Analyze the logic circuit to determine the expression, and then use the logic expression to derive the truth table from it. So this was where I added the extra slide. I should have done that on the earlier one, but you live and you learn. Okay, so we have A. If A goes through the inverter, that becomes A bar. And in my AND gate here, I'm ANDing A bar with B, and so that is expressed as multiplication. Here, we have C coming in, and so they're going to get ANDed together to give us A bar B, C. Here, this is inverting C, which is going to give us C bar, and this is tied to B, so this is going to be B, C bar, and then our output of the whole thing is added together, so A bar, B, C, plus B, C bar. Then we need to do our truth table. So that's our logic expression right here. And so we have A, B, C, and then I have no idea why I did that, but so we have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. And we need this to go high at, looking up here, 0, 1, 1. So it's going to go high right here. So 0, 1, 1. And then we have like B, C bar, which means that the A doesn't matter. So it would be A bar, B, C bar, and also A, B, C bar. In other words, the A doesn't matter. So this would be 0, 1, 0. And this would be 1, 1, 0. And then it's going to be, I think there's another one in there. There we go. So it should be 0, 0, 1, 1, 0, 0, 1, 0. 0, 0, 1, 1, 0, 0, 1, 0. Same problem as we did last time. And so there we go. A bar, B, C, and then B, C bar. And 0, 0, 1, 1, 0, 0, 1, 0. So same process, like you end up like in the same place. So one of those methods you're probably gonna like a lot more than the other, but they're both useful. Like they both come in useful. And sometimes you might do like one piece of the process one way in a circuit, or break it down, and you just got to dig deeper. I know with looking at some of the issues with the circuits from the random number generator, one of the things I did is put like probes in to different places so you could like test the output of the different gates. And I think it was Tyree's circuit, like there wasn't anything visibly wrong with it, but when I hooked up like a probe on the other side of the AND gate, like the AND gate wasn't ANDing the stuff together. It wasn't doing what it was supposed to be doing. And so that helped me, figure out a way around it. But that completes this lesson, and then we will pretty much work through the PLTW activity as is with minor modifications.